interesting part of our model. We can also use textual languages to describe.
It's no problem, I can use. And then on the internet they will also hear. Okay. So, I'm much louder now. We can use this textual notation to describe the interesting parts in our models. And then if we define these patterns, we can find these patterns in the model. So for example, we found this pattern here and here. These were called the match sets of these patterns. And then we can use these patterns to process our models. For example, we can modify the model, we can create other models, or we can generate artifacts from it. For example, when you want to use your models for source code generation, that is a very, very useful methodology. And you can also use these models to transform one model to another model, and you can just make a chain of models. After that, you reach, for example, some certain goals. I will show you some examples for also that. So we talked about models, but we also have to talk about model-driven engineering. So it is, the terminology is sometimes very confusing. There are many model-driven thing in the world. So, but from our perspective, they are quite similar now. So I will just use them interchangeably now. But if you hear that model-driven software development, model-driven engineering, model-based systems engineering, or software engineering, they are based. All of them are based on the same principles and same methodology. So I also have to emphasize there is the so-called model-driven architecture. That is something different, because that is a design methodology proposed by the object management group that relies, that is actually a standard that relies on platform independent models and platform models. And by using MDA, you can generate this platform-specific model that can be used this way, for example, for code generation. So it's something different. I will talk a little bit about that. And there is also a related concept that is model-driven testing, that is called model-driven testing or model-based testing. It's when you use models to generate tests in your system. And just some words about model-driven architecture. That is a software design approach for the development of software systems, and it provides a set of guidelines. So you have at first the platform independent model from which you will you extract, you put some more information, platform related information, and by giving this additional information, you are able to generate the code for your platform, and then you get the application, you will get the implementation. So what do you need for model-based systems engineering? There are three main pillars. You need modeling language that defines the elements and the relations, and you need the syntax and semantics. So what you can do in your language and how it will behave, how you can understand it. And for example, we will learn UML and SysML for this purpose. You also need a development methodology. So it defines the stages, the steps of the development and analysis of our system. And these methodologies define how shall the model be built So, for example, sysmod is such a methodology. We will just go into it in a few minutes, so you will see that there. But there are many other methodologies uh, that are available, and you also need to support. So, for example, we will use in the third day we will use Yakindu. That is an open source tool, not for systems engineering. It's mainly for behavioral modeling. But there are many tools for systems engineering. For example, Magic Draw, that is also used by NASA. Enterprise Architect or IBM Rational Rhapsody that are used by the automotive industry in Europe. And there are many, many other tools, and there are also some open source tools. But that is still not enough, because there are two more extra aspects. You must have domain knowledge about, you have to know what to model. And you also need a team that is capable of creating good models. They have the ability to develop the models. So that's what you really need for model-based systems engineering. And let's see the different models, different languages that we can use in systems engineering. We have static models that these models define the static aspects of the system, including data, architecture, and many other aspects. And we can also have dynamic models. They will define or describe the dynamic behavior of our systems. So it's some kind of execution of our system. For example, state machines are for this purpose. There is another categorization regarding of the models, and this is mainly based on their level. So at the top level, we have the engineering models, such as UML, SysML, and we can have also domain-specific languages, and I'm sure that you met many of these domain-specific languages so far. So we use mainly the engineering models, but below that there are the high-level modeling formalisms such as data flow, Petri net, that have some formal semantics, but they are still quite high level to be used by the engineers. And on the bottom, there is the underlying mathematics that is defined with the help of, for example, automata theory, or other mathematical equipment, mathematical tools that you can use to precisely express, to precisely define the semantics, and to use verification. So in this level, you get the verification algorithms that are used to analyze your models if they are constructed correctly, and so on. And what you can see is that going down, we will get more precision and less abstraction. So here is the most abstract level. That is what you use in engineering, and that is the finest, the most detailed part that is used in analysis. And there are other categorization, because you can have general purpose modeling languages that can be actually applied to nearly any domain. And such modeling languages, for example, state machines or Petri nets and UML, SysML. So you can use them for everything. But there is another kind of other family of languages that is called domain-specific modeling languages. They they are specifically designed for certain domains. For example, AutoSAR is designed for the automotive industry. HTML is designed to be used for describing web pages and designing web pages, and they are very good for that purpose. But just these languages just focus on a certain domain and for certain purposes. And we also need development processes. I'm sure that many of you are familiar with the traditional Y model. Who has ever seen this figure before? Please raise your hand just to. Oh no, not so many. Okay, then I will just go into the details. So this model just starts by the requirements engineering phase. Then we go to the specification. Then we create the architecture design, component design, and then we will be able to do our implementation. And each phases here has a corresponding phase in the analysis and testing phase. So from the component design, you will do unit tests that you will run on the implementation. From the architecture design, or according to the architecture design, you can develop your integration tests. From the specification, you will get the system tests, the system level tests. And according to the requirements, you can develop the acceptance tests at the final stage that will be used at the final stages of the development. So this is what the critical system industry uses for quite a long time ago now. So if you are developing cars or planes or railway, you have to follow these steps. But the promise of model-driven engineering is that we can modify this traditional Y model and we can get a simplified model by using early validation of the systems model, and we will use automatic source code generation. So we try to automatize as much as we can. And this way we will get better quality. We need actually tool support for that. And this way we will reduce the development costs. So here I can see the model where you manually design your requirement specification and architecture design, and we provide you use transformations, model transformations, and various generation techniques to make this part as automatic as possible. So this way you will get a much more efficient methodology. And so how to apply model-driven engineering? Actually, there are various phases there where you have to use, or where you can use models. So I do not know if you can see it on the last row, the figure. So actually at first we create the requirement specification. Then we verify our requirement specification, and we create, according to the specification, the system design in a model-based way. Then we can simulate actually our models, our system. We can analyze our system, and we can actually extend it with variations and analyze the different variations that are available, and then we can you can choose the best one, the best configuration, the best variation that you should use in your system. And then also you have to create test models, and if you created the test models, then you can generate test cases that are used to analyze your software and test your solution. So we can get a documentation with the help of MDA, and model-driven techniques support requirement specification and also support the system design. So it will be a well-documented process. We can use models for synthesis. So we can synthesize some parts of the system, such as design or the whole application or other artifacts. We can do verification on the models at a very early things later. And we can also do some analysis, and we can analyze and simulate parts of our system at an early stage of the development, and we can get some results and decide if our system is the one that we want it to do. And we can also integrate analysis. So it works in a way that you have the engineering model, so for example, SysML model or other models. And from the SysML model, you can generate a formal model, a mathematical model that can be fed to the analysis tools, to the verification tools. And they will do the analysis, they will provide the results that had to be back propagated to the engineering level to support the engineers in the understanding of their system. And maybe if they need, they can make some, they can fix the design at an early stage. I will show you some tools for this purpose. So just to summarize the various synthesis approaches that can be used with models. So at first, if we use platform independent models and we provide the platform model, then we can get the platform specific model from which we can generate source code. For software, we can generate hardware description and other kind of things. We can get configuration of our system, so we can synthesize various configuration parameters and settings for our application, for our hardware, or for anything related to systems. We can generate test cases from our models, and we can also generate a monitor program that will be run together with our system, with our programs, with our logic. And by using monitoring, we can detect runtime problems during the operation. So we can monitor our application, our system. So what we learned is what is a model. That is an abstraction of the real world. It is built from elements defined by the modeling language, the so-called meta model. We model systems because for various purposes such as documentation, we want to verify our system, analyze, and we want to use some kinds of synthesis. We need for modeling language, a methodology, tool support. You also need to have some domain knowledge and expertise experience. There are various types of models to be used, such as general or domain specific, engineering, or mathematical. And we can focus on modeling the behavior or and the structure. And I also showed you some techniques to process the models by means of model queries and transformations. So, do you used to have breaks? How do you used to have the presentations? Do you need break, or when should we have a break? We can go? Okay. If we go so fast, you can go home early. But you don't have to hurry now because Copa America is over. So, did you watch the match yesterday? Who watched the match? And the others? I thought that in Brazil everybody watches football. Actually, well, actually, I had many misconceptions about Brazil because I also thought that it's always hot here. And then I arrived to São José dos Campos, and then I went to Campos de Jordão, short and t-shirt. Actually, everybody was wearing jacket and long trousers and pullover, and they just looked at me. Oh, what I'm doing there? Actually, it was very, very funny and very, very cold. So let's go on. I will just show you some development methodologies. I won't go into the details of all the methodology because I will give you the slides, and you can just, whenever you will go and develop model in a system in a model-based way, you can use the slides as a general outline of how to use modeling. But I will show some of them, and I will start with the so-called Iconics process for software because it's very simple, and this is a kind of way how you can develop in models in an agile way, how to use models in an agile way, and that's not so often that these design approaches support this kind of thinking. So in the Iconics process for software, you have a part for the dynamic modeling and also for the static modeling, from which you will be able to construct, to develop your code and unit tests and your implementation. So it has various phases. The dynamic part starts with use case modeling. On next step, you do the robustness analysis, from which you will just refine your use case models, and you will get finally the sequence diagrams describing the interactions of the user and the system. And in between, you also develop your static models continuously, your domain model, and from which you will derive and finally reach the class models, the class description of our system. So we start with the requirements engineering phase. We will, in the Iconics, you have to define your functional requirements. So define what the system should be capable of doing. And you also develop your domain models to understand the problem space. So it's a very abstract model. Here we are here, this part of the process. And you also develop the behavior requirements. You define how the user will interact with the system. And at the end, you have the requirements review phase, just to make sure that the use case matches the expectations of the customers. And then comes the robustness analysis phase, when you do some assumptions, preliminary assumptions about the design, and you start to design the technical architecture, and you try to evaluate the various possible designs, architectures, and so on. So it's somewhere between the what and the how. So at the first we had also what you want to do, what you have to do, the requirements, and here you have the detailed implementation, and this robustness analysis provides some steps to bridge this gap between the requirements and the design. And according to the robustness analysis, you update the domain model, you discover missing classes, missing elements, you have to correct ambiguities, and you can also provide attributes to the domain objects. And you will also name all the logical software functions. And at the end, we have the preliminary design review. And then we develop the detailed design by using, for example, sequence diagrams to show how we should implement the various use cases. We will add one sequence diagram per use case, and we can also allocate behavior to the classes. And in between, we continuously update the domain model with the new information. We add operations to the domain objects according to the sequence diagrams. And then finally, our goal is to reach some representation that we can implement. So for example, we will reach a static model class diagram and so on. And then we will close this phase with a critical design review. And then we implement our system. So we do the coding and unit testing, and the integration tests are based on the use cases and on the sequence diagrams. And then execute a code review and you update your models if necessary. And this is an agile approach. That means that at the end you can still go back to first step and modify your systems and your models. Iconics also defined a roadmap for systems engineering. So this is a more general approach, focusing on not only the software aspects. And it starts by defining system requirements. Then we model the system block structure and the behavior. Then we will define constraints and parametrics to be able to simulate our system. And according to the results of the simulation, we can still go back and modify our design. And if the simulation and the analysis is successful, then we go on to implementing the hardware and software and test them together. So system requirements, there are two main aspects of system requirements. One is the functional requirements that define the capabilities of the system, and you also have to define non-functional requirements related to our system, such as performance, reliability, availability, and other non-functional, extra-functional requirements. And we organize the requirements into hierarchies. We will learn how to do that. We will learn that today. And then we will allocate requirements to system elements. That's actually an ongoing process as the model is developed. And modeling the block structure is started by modeling the problem domain. Then we will define the blocks. And then we also have to allocate requirements to blocks to provide some kind of traceability in our system. And then we will also define the ports for communication. And in between, we also model the system's behavior with the help of use cases, and we allocate the requirements to use cases and also model the interactions for the use cases. And the finite state behavior is also modeled, and we also have to allocate the requirements to the state machines. And then we will reach the complete behavioral models. And as I mentioned, we have to define the parameters, constraints, and other things to be able to simulate our system. So at first, we will define constraint blocks to define those constraints that are related to our systems. And we can also add scripts to these blocks to be able to make them executable, and we can then run the simulation. So you defined the constraints related to the system that you create, but you also have to define the parameters of the environment that you want to use during the simulation. And you can do it in this step, and by providing all this information and designing these models, you can simulate your model, and so you can run it in a simulator and get some simulation results. So that was the Iconics approach, but I mentioned you also that so-called SysMod approach that is also related to SysML, and this is also design methodology that it is actually very detailed. So if you're interested, I will just give you some pointers to some books and that can be read, and they provided a very detailed methodology. Now I won't go so deep into details because even at an abstract level, it has many steps and stages, and actually each stage can be refined, and it has many sub states actually. So the SysMod approach starts by analyzing the requirements, and the outputs of this phase is the project context, the requirements, the system processes that describes that is used to describe the system, the processes inside our system. We also provide the use cases at the end of the requirement phase, and domain knowledge. You will model the system context, and you will also provide the glossary. Glossary serves to help the interaction with the stakeholders, with the customers. So because I do not know how much experience you have in systems engineering or in software development, but it's a problem in many cases that you use a different vocabulary than your customer, and this glossary tries to bridge this gap between the engineering vocabulary and the vocabulary, the words and the expressions that are used by the stakeholders. And in the requirement analysis, we have various steps. So at first, we described the project context to provide some basic understanding. Then we derive the requirements, we determine the requirements, and according to the requirements, we can also model the context of our system and provide the use cases that are very useful, because use cases are easily understandable by the customers, and we have to model the domain knowledge and create the glossary. And then in the next phase, you create the system design. The input that you use is the use cases and the system context. And what you want to develop is the system structure at the end. And the steps are, you will at first model the system and actor interaction. According to this, you derive system interfaces, then model system structures, and then derive state model. Actually, here SysMod defines this process in a way that you finally get this model description. So then you can decide if you will use code generator, or you will, let's say, implement your system manually. So it will just, the SysMod approach stops here. This is a problem sometimes. So I will also show you another approach that really wants to bridge this gap, and that is actually the so-called platform-based systems design. So this SysMod approach, as you could see, it's very detailed, and it was started from the beginning of the development process. So if you just want to start a project from ground, it provides you many detailed steps. So it's very useful, but it will not go directly. It will not lead to the implementation. So that's why I will show you this so-called platform-based system design approach that starts by expressing and defining the requirements. Well, actually, here you can also use this requirement analysis phase, those steps that were defined by SysMod. And from the requirements, you create the functional model and the platform model. And that's a very important thing, this platform model, because you will use those hardware and those elements that are defined, for example, by your hardware library. So you, for example, if you design satellite and another satellite. Actually, you will not design all the hardware. So you will definitely buy some hardwares, microprocessors, microcontrollers, and so on. And you have a library for that that contains all those uh, components that you can use in the design. So, and you have to model also the platform, and that's a very important step. And from the functional model and the platform model, you will do the hardware software allocation. Here it's very important that you have to take into account the fault tolerance and safety related issues. So this is the part where you can take into account that how fault tolerant your system should be and other aspects in the allocation. And you can also design your system in a redundant way to improve, for example, the reliability, the fault tolerance, and you can take this information into account here at this phase of the development. And then you will get the architecture model. From this and from the functional model, you can define the component level behavior, the behavior of each component, and also you can model the configuration of your system. And from the component behavior model, you can get the source code by using a code generator. And from the configuration model, you will just transform them and use code generation to get the config files. And your compiler and linker will provide the binary code from all these models that you can run on your system. So I think these are those additional steps that are needed to reach the implementation at the end. So I will also talk a little bit about the advantages of model-based systems engineering, and also about that how one can introduce these techniques in a new environment, because it's very far from trivial to use these techniques and introduce them. So I will start with a survey from the automotive industry with 180 participants from 14 countries. That this survey included the management team, developers, research and development teams, and what they found is the main characteristics of modeling. So they found that in the design phase, the development costs increased, actually 30-40%. At the verification and testing phase, there was a reduction of 40% in the time and cost. And if they use code generation, actually 40% of the participants stated that more than 90% of their code is automatically generated. And here the cost reduction was very close to 50%. And what they found is that the return on investment is in 3 years. So you have to wait. It's not an immediate change, but it's really worth waiting. So you have to be a little bit patient. And the reason for that is that 60% of the design errors are revealed in a very early phase of the development. And another important aspect is the virtual prototyping. And what they also found is that companies who have just started with model-based development, they had a small modeling degree in the area of 5 to 20%. But those companies that had more than 5 years of experience, actually, they reported a modeling degree around 90 to 100%. So this still tells you that you have to be patient with these techniques. And if you are interested, you can read this paper. This is written by a very famous professor from Germany. So it's a very good reading. So, and I mentioned you that by using model-based design, you will you will get better requirements analysis, and you will find much more defects in the requirement and design phase, and you will have only fewer defects that will be revealed at the unit and integration testing phase. If it is compared to the traditional industry average that is actually measured by the Software Engineering Institute, actually you will have find more defects at the later phases of the development, and it will cost a lot. So this is a huge advantage of model-based systems engineering. And if you're interested, you can find this information in this paper. And modeling and model-based techniques have some positive and negative effects too. So, for example, just to tell you something that is not so good, is that there was a huge survey. You can also find here this figure in this paper. There was a survey, and they found that, for example, confidentiality is a problem in many cases. So because in a model you provide all the information, and if you have to work together with other companies and you reveal the models, you give them your models, they will know everything related your system design. So that can cause problems actually, and also sometimes the efficiency of the resulting code. So if you use code generators, sometimes you will not get the most efficient implementation. You can do that. So actually, I know company, and they developed their own code generators that no developer can write such a fast code like their code generator could. But actually, this is not so typical. So it can also be a problem sometimes that your implementation, your generated code is not as efficient, not as optimal as if it was developed by a developer. But regarding the quality, reusability, traceability, reliability, maintainability, actually modeling techniques have a huge advantage. So and also sometimes the standard conformity is also sometimes a problem. So there are many advantages, disadvantages. You have to be aware of all these aspects of model-based techniques. And I will talk a little bit about how one can introduce model-based systems engineering in, for example, in a company, in a project. So in a traditional company, you have the management, the development team. And when you introduce MBSE, model-based systems engineering, you will need some modeling advocates. And their role will be to introduce an abstraction layer in order to reduce the efforts and in order to provide understandability and comprehensibility. And these models must have a clearly defined semantics. That is very important. And also the modeling advocate will introduce the separation of concerns. So he or she has to provide the structured view for the engineers, depending on the particular aspects of the problem. And the transition from traditional to this model-based approach will sometimes disturb the established product development process. But the promise is that after an initial phase, your productivity and quality will rise. So there are many problems when you want to introduce MBSE. So For example, the concrete semantics of a model is often implicitly redefined by the individual modelers. People like to ignore the semantics. They like to interpret the models as it is comfortable for them, and this can cause serious problems when you apply model-based techniques. And this is a problem because the adaptation of the semantic is not done systematically in many cases. And there is also a problem that the costs of creating correct models in the modeling tools that fulfill the intended semantics of the code generators, it is this cost is very high. So it can really make things really slow and really painful. So there is another way to introduce modeling techniques. So you can, instead of radical paradigm shift from the traditional development method to MBE, you can have strategy about a gradual, incremental introduction of these techniques. So this technique is called MBE micro injection. It defines manageable introduction steps within one development sprint with a limited size, and it also supports an accurate monitoring of the introduction and the costs. What you need for this is an adequate tool support. That is very important, because you have to support the coexistence of these model-based techniques and also traditional approaches. So you have to manage them together. And you also need some kind of modeling language support, the so-called meta model or taxonomy about the system, and that is what the engineers will use. And if these micro injections are well designed and introduced, actually, luckily, no essential model-based engineering paradigm needs to be validated, violated, or omitted. And to do this, you need this MBE micro injection designer who will set up an action plan composed of MBE micro injections, and each micro injection is assigned to a short integration sprint with a measurable output. And the goal is to avoid disturbing the daily business. So at first, you can apply it in parallel to the traditional solution. And if it is successful, then you can replace the established solution, or if you found problems, then you can adjust your MBE micro injections to fit better into your processes. And if these MBE micro injections are composable, so if they are related, if they are based on the same mathematical foundation, then you can combine them together for larger system design. The MBE micro injection designer must have knowledge about the applied development environment and also about the information that you want to model. So it's very important, because if there is a change in the environment that used to represent a disturbance for the developers, because they usually do not accept an additional tool which they have to use in parallel to their well-known development environment. So, but they appreciate new features in their development environment. So, for example, if you want to use MBE micro injections, then you can, for example, instead of using a feature-rich UML editor, you can use just a sub-editor with smaller features, with less features, and this way you can support the introduction of model-based techniques. But also the MBA injection designer has to know the domain that is the target of the development. And most developers have already in their mind internal meta model for their approaches. And the goal is to turn these internal, implicit, and hidden knowledge into a formal, explicit model. And this way we make it available for everybody. And this is supported by rapid prototyping, where you also need a meta model prototype, a concrete meta model representation that reflects those taxonomy and those things that are needed to define the proper abstraction of modeling. And this meta model should be based on the development team's terminology. And you can create model prototypes. So if you have the meta model prototypes, you can use them and create the model prototypes that are conformant to the meta model. And this way you will get some experience that can be used in later stages. And also you need a model editor prototype and a code generator prototype to support the development. And also the microinjection designer has to introduce the paradigm of separation of concerns. So in modeling and in model-based engineering, we use the single source of trust SSOT paradigm because it is good to use information referencing instead of information copying. And how you can imagine that we have these two information for sources, two models, and we want to use this information B that is in model B, and we want to use it in model A. It's very important that we do not copy it, but we make references, and that is the essence of the single source of truth paradigm. So a simple rule here is that every SSOT has a single author, and this is the author is able to edit this the content of this model. And each SSOT has a series of consumers. They use and process the information, but they are only able to read the model, and you cannot modify it. So you just divide your information into parts, and each part will have a let's say somebody that can edit, and the others will just use the information that is edited by the owner. And it is very, very important to find the right abstraction layer to be able to focus on the relevant informations. And actually these micro injection designers have a huge role in assuring finding this right abstraction layer. So this was my general introduction of modeling techniques and so on. I think we can have, let's say, a 10-minute break if it's good for you, because I will just lose my voice and I also have to drink a coffee. So 10-minute break and then we continue. Is it good for you? But we are very fast, so you can go home very early, I promise. Okay, thank you. Then see you in 10 minutes.